What's that? Oh, that's right. Oh, I didn't. Yeah, they're optional, totally optional, but it's nice. It's been a long time since I've seen everybody's face. A long time. But it's cool if I'm not seeing your face too, so no pressure. Totally good. Completely stay comfy, stay what you need to do. Yeah, I was telling Kayla, I thought, shit, I need to trim this beard up. It's like a hobo beard, but I'm kind of a hobo beard guy, so.
What do you mean?
What?
What do you mean?
It's just, I don't know, that's what my wife tells me. Just,
It must be right because she says it.
yeah, I mean, just, you know, just unkempt. Lack of concern over appearance, possibly.
See you in the summer.
Yeah. Yeah.
Oh my God.
All right, my friends, let's just settle in for a few minutes. I'm feeling really good, and I want to just get focused. And we could just get in touch with our bodies and gently progress to noticing the breath. Find yourself lost in thought. Notice the thought itself, what it's like to be lost in thought. Gently return to the breath. And then just gently coming back to real analysis class. Howdy, Michael. Well, do you have any questions for me before we begin on the current homework that is, in theory, due on Friday?
Wait. Yeah, let's do Friday.
What did I say?
I think it was originally due Wednesday, but I would take
Oh.
it being due on Friday.
Did I say, yeah, let's do Friday.
Okay.
It feels like that's probably what's gonna work best anyway, right? Okay, all right. Probably. If you want us to ask questions, we have to start it. So make it Friday. Okay, that's fair enough. Fair enough. Oh, Michael, your other assignment, it was electronic submission. I have to just email it back to you, but you got perfect on it, so there's no comments. So no questions yet? Okay, that's cool, and that's totally cool. That is great, because I'm so excited about what is happening today. Because if you did the reading, you might know why I'm excited. The section 3.1, I would recommend reading 3.2 for sure. We're going to start on this today, and if you can inch up to 3.3, that wouldn't hurt you. A lot of this is going to be new, very new. As we talk about, unless you've had like the ideas of open sets and closed sets before, so how many folks have had these in their lives? In complex, we had some of this. So no? Okay, cool. Well, this is fun. This is really neat stuff. So that's all part of the topology we're going to talk about. But let's just start off first with one of the great examples in real analysis. So I should put the Cantor set. So we can call it C. Yeah. Sure, that sounds pretty reasonable. The Cantor set C. So the construction of this set is stage-wise, and we have infinite number of stages. We start with the closed interval 0 to 1. We'll draw this. And this is a recursive procedure. And what we do is take the existing stage and remove the middle open third. So open here, is just the open interval that we've always known. We're going to generalize that, but we're going to move to step 2, where we pull out that middle third. So this is 0, 1/3, 2/3, 1. That's stage 1. Now do that to each part that remains. So remove those middle thirds. Da, 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 da. Starts looking like H's, but then this is 0 to a 9th, 2/9, 1/3, 2/3, 5/9, 6. No. Let's see. So that's 6/9, 7/9. Okay. 8/9. Did the math wrong. 1, etc. Continue forever. We are going to say that the Cantor set C, and let's call these C0, C1, C2, on down. The Cantor set is equal to the intersection of all of these sets. In some sense, just what you're left over with at the end. A collection of points. This set is crazy. It really is. Just like simply on its construction, it's really beautiful, simple construction, a little bit mystifying. But gosh, I don't know how far we'll get today because there's a lot to talk about here. So the first thing is, let's just talk about what's left. And I guess that's really the only thing to talk about. What is left after we remove all those thirds? So let's do a computation. Total amount removed. So in stage 1, I removed a third. How much did I remove in stage 2? 2/9. How about in stage, what would be the next removal?
4/27.
What was it?
4/27.
4/27. Yeah, beautiful. Because you're going to cut each of these into a third, which is a 27, because they're each a 9th long, and then take out that middle third. So, and there's going to be 4 of those middles, so it's going to be 4/27, and then that looks like a pretty good geometric sequence going on there. Series, excuse me. Let's add it up. How do you add up a geometric series? So the sum of a geometric series is, we talked about this, the first term over 1 minus the common ratio. And notice that the common ratio is 2/3. So 1/3 over 1/3, 1. We remove everything. We remove a total length of 1. So what is left is just a dust of sorts. Just a dust. There's a thing called Cantor dust, and you could call this Cantor dust, but Cantor dust generally is this more 2D version of this that we'll talk about, which is pretty cool. So total removed is this, so total length left is 0. We're going to measure up everything that's left. There's nothing left. Where do I want to go next with this? Okay, so it's got no substance to it. But how many things are in there? Let's figure that out. So what is the cardinality of C? Ooh, pen dying. Let's do the cardinality. And this is a cool trick that you've already used and seen, and it's amazing how actually prolific this tool is. I don't know if prolific is the right word, but ubiquitous, something like that. Okay, so God, I'm getting lost. I'm really in a good mood today. I really feel good. I'm really happy about spring. Just doing good. So what is cardinality of C? And to answer that question, we have to come back to this primal staging over here and think about how do you get to a point. So somewhere down here, at the end of all time and past it, wherever infinity is, down here there's a bunch of dust of total length 0. How do you get to those points? Well, you start off here. So let's say I wanted to get to one of these points down here. I'll call it X. I could navigate you. I could say at each stage I'm going to give you a left or right direction, and you can follow that branching pattern all the way down to this point. So this one kind of looks like it's over here. So I would say, first off, let's write this up. Navigate through the stages. Let 0 equal left set. Let 1 equal the right set. And so if I wanted to get down here, the directions would be like this. First take the left set, because it's clear, this seems to clearly be in this left side, so that's a 0. And then I would actually have to go to the right set, it looks like. So that's a 1. Do you see how this is working? And then at every step of the way, I tell you which half you need to go to. And the L and R's are going to correspond to 0s and 1s. And so each of these points down here, and create a direction decimal, direction binary fraction. There we go. Let's cut to the chase. So it goes like this. 0 point, here's the stage 1. And here, let's see, what do we got there? 0. Here's stage 2. And then, depending on what I have to do after that, I don't really know, but this gives me a series of left and right directions. So this is just an infinite sequence of LNRs. We've seen this before. I'm constructing a binary fraction between 0 and 1. Think about this. There is a one-to-one correspondence between these numbers and those numbers. Each one of these numbers is a direction to a point. Each direction to a point is one of these numbers. So there is a one-to-one correspondence between these numbers, i.e. the closed interval 0 to 1, because that gets them all. If you want 1, you just fill that all in with 1s. So let me just make a little note there that 1 is this number. In the same way that this number, and remember we're in base 2, so if this is confusing, just remember this is all base 2. This number in base 10 is also 1. You could prove that with geometric series if you wanted, because this is just a half plus a fourth plus an eighth, so on. So literally, it's first term in the series, common ratio 1. You could prove that just as a geometric series. And the points in C.
Um,
Yes, sir.
so would be an issue because, like, since the 111 rounds up, couldn't it be like, I don't know, I have one that ends, that you start at 1 and then go 0 the rest of them, and then another that goes 0 and then 1 the rest of them, and wouldn't that ramp up to 1?
So wait, so give me your first number again, Noah.
Okay, so let's say the first one, you start at 0, so, and then the rest are just 1s.
So like this. Oh yeah, you're right. Actually, not quite a 1-to-1 because of that possibility. So yeah, for example, this point, this set right here is actually equivalent. These two are equal to this. So let's say, yeah.
And just to double check, that's because you're taking the ceiling?
Ooh, when you say ceiling, well, explain to me what you mean.
I guess I'm asking why we know that those are equivalent.
Oh, okay, gotcha. So this number here, Kayla,
Yeah.
this number would be 1/2, 0 1/2, right? No halves.
Yeah.
Plus a quarter, plus an eighth, plus a 16th, plus blah, blah, blah.
Okay.
And then if you added up that geometric series, first term,
Okay, gotcha.
over 1 minus common ratio, now I actually have to see this. This is starting to concern me a little bit. So wait, so that's over 1/2.
Which is
That's 1/2. Yeah, that's 1/2, and this is 1/2 as well. Yeah, makes sense. Yeah, so it's not a 1-to-1 correspondence. You're right, Noah. Huh. So this number here. Ooh, let's take a look at this. Let's just see. Let's look at this first direction, or second direction. So that one right there says take the right set and then stay left the rest of the way. So this would correspond to 2/3 in the set. And then that one would say take the left branch and then stay right the rest of the time. So wow, so this one would actually correspond to 1/3. Pretty good point. Yeah, okay, so hold on.
So it's because their address is not just, we're not using them as binary, we're using it as an address.
Yeah. As an address, they are not unique addresses. So let's see here. Okay, how about this? Oh, he's leaving. He's leaving. Each one of these I won't say, I'll take out this 1-to-1 correspondence, because I think that's the bad part. Each one of these numbers corresponds to a point over here. Right? And each point over here can be written as one of these numbers. So if I look at any particular number, now, oh damn it, Noah, get back here. So if I look at any particular number in 0 to 1, any of these, it corresponds to one of these points. So what I'm backtracking on, Noah, is that it's not a 1-to-1 correspondence, but there are as many points here as there are points in here. At least. At least. And they are not unique, but each one of these points is absolutely corresponding to one of these, and vice versa. There's some repetition, for sure. For example, what's this point right here? Well, let's see. What does that point correspond to over here? That's just literally 0, right? So that corresponds to, so in C, let's see here, 0 to 1, that corresponds to 0. How many other ways are there to get a third? I don't think there's another way to get a third other than this. Go left, stay right. That corresponds to a third. Let's see. Is there another way to get a third? I don't think there's no other way to get 1. I think,
So.
yeah, go ahead, Michael, yes.
I was looking it up because I remember watching a video. I think you're supposed to use base 3 for this. I can't say why, but.
Oh, well, the endpoints definitely correspond to the ternary expansions, ternary fractional expansions. But here, I'm positive this binary will work, but there is a relation to the ternaries, so you're not at all off base with that. I still feel like each one of those numbers corresponds to a unique point over here. And I don't know how it can't. That's the part I'm thinking. So even though these representations over here are, well, wait a second, no, actually, I don't think there is another way to write these numbers. So for example, this number right here, this example you came up with, the 1/3,
Yeah.
there's no other way to write 1/3 in binary.
Yes. Yeah, I'll agree with. I mean, that seems correct.
Or wait, that doesn't correspond. No, but this is the precise oh shit. Wait. Let me, okay, I think I know what I need to say here. So, each point in C corresponds, I think this is what we need to say, to a number, don't write this down yet, in 0 to 1. And there might be, yeah, how do we reconcile that? How do we reconcile, just what are the words to say here? Great question, Noah, because you got me pretty floored, literally floored here.
Is this like when you would talk about well-defined, like 1/4 is equal to 2/8 kind of thing? Like
Yeah.
you can write them in both notations. Is that what you're trying to say?
Yes.
Like
yes.
not necessarily that they are 1-to-1 because there's repetition, but that they, if it exists in 0 to 1, then it exists in C.
That's for sure. Okay, that's a nice way to say it. That's a very nice way to say it. That each, I like that, Kayla. And each point in 0 to 1 gives you directions to some point in C, corresponds to a point in C. I guess setting up the bijection that we would need for cardinality, we might have to kind of think a little more carefully about that. But like, how else do you get, so this is a really, I've never even thought about this, but this is a really cool problem because these are the same number, but they are completely different directions.
What you could do is make it 0 to 2, and then just if you round up, you add 1 in the very top part of the fraction. Although I think in that case you can say 1.
Yeah.
I think you should be able to get every other number to do that.
To say that again?
So instead of making it 0 to 1, make it 0 to 2.
This is what Michael was suggesting, so use a ternary expansion? Oh,
I
hi Anna, we'll probably have this figured out.
I don't know what a ternary expansion is.
So that means you've got base 3?
No. So keep it in base 2.
Oh.
But if you have to round up, just put a 1 in front of it. So for like 1/3, it would be 1.10000.
Oh.
And then,
But that takes us out of that closed interval and moves us, it's gonna fragment the numbers into 2 sets that like, that scares me.
On the book, it
That's
does
so
say,
funny.
on the book it does say 1-to-1, so it is one-to-one, but
I remembered it being 1-to-1 because that's how we know the cardinality of C.
Yeah.
Because it must be uncountable.
It's definitely uncountable.
Yeah.
Okay, and that's really all we're trying to freaking get to.
Well, we can get to that without proving 1-to-1 here,
But we also, okay, because we've decided that it's dust, that means also that it must be the same size as R, which is what we're trying to say.
Wait, explain that.
So when you look through the proof in the book,
Okay.
it
What
says-
page is that on?
Am I making shit up?
85.
No more than I am.
86, yeah, 85, 86.
Okay, yeah.
At the bottom of 86, it says first C is uncountable with a cardinality equal to the cardinality of R.
Definitely.
Which makes sense. And that also makes sense because there's an uncountably infinite number of values within the closed set 0, 1.
Yes.
And since we're saying that there's a 1-to-1, then also there's an uncountably infinite number in C. Know what I'm saying?
Yeah, I do, and I agree with you. I agree with you. Wait, they point us to an exercise. What is the exercise they're pointing us to? Exercise, oh,
I think that's the one we did.
that's one we did a long time ago. It's not like, okay, I'm not gonna waste any more class time on this. I will address this and get you all a decent answer. But we do agree, yeah, God, yeah, now that's really worrying me. How do we know things aren't smashing together, right?
Well, didn't it say that in the proof? I thought it said somewhere that there is, hold on.
How about this? Each number in here corresponds to a unique point over here. That is true. That cannot be argued. So there are at least as many points over here as there are numbers in there. How about that? I think I've just been searching for it. You feel good about that, Noah? Okay, awesome. The man's happy. We're good. Shut this show down for a bit. Okay, so the cardinality of C is C, the continuum, which is the so that's a different C. I'll make it a little fancier. That is the cardinality of R. So even though there's nothing here that we could grasp or look at, there's as many things there as there are points in the original interval. Somehow. And what's another thing we know? Look at what's left here. The only thing that's left at each stage are closed intervals with rational endpoints. Right? So it seems really amazing that this ends up uncountable. Really quite strange and phenomenal. Okay, let's talk about the dimension of this thing, because that's what I was like super stoked to talk about. So dimension is a really like one of my favorite topics in math, and there's probably half a dozen different ways to actually measure dimension. A really simple way that just kind of works for basic math linear algebra is dimension is the number of pieces of information required to describe the location of something in a space. So 2 dimensions, you need a left, right, and a backward, forward. You need 2 pieces of info, no matter how you do it, right? Even if you've got the plane and you've got polar coordinates, you still need 2 pieces of information to describe the points there. And so, and like I said, there's a number of very interesting ways to do this. But when we come to creatures like this, those methods fall short. Because this feels like, well, it certainly doesn't seem 2-dimensional. It seems like it's at most dimension 1. But there's nothing here. There's literally nothing here. I can't move from one point to the other Is it dimension 0? Is it just a point? Well, let's figure it out. So dimension, one way to define it is, I guess you could kind of call this scaling dimension or self-similarity dimension. That's a bit what we're doing here. The other methods are box dimension, Hausdorff dimension, many others. But these are the most common, the three that we're going to talk about here. So let me show you the game and then get the formula out. Start off real simple. I got a square. Nice old square. We know that's two-dimensional. So whatever we do, it needs to make sense with things that we already agree on and understand. So take this square. Let's say it's unit length on a side. Doesn't really matter, but it'll make thinking about this a little easier. So 1 by 1. I'm going to cut the square into a half. So I'm going to cut each side into a half. How much do I have to expand this square, scale it uniformly, so that one of these pieces becomes the original square? How much do I have to scale this by so that one of the new pieces becomes the original? Like, what's the factor? So notice if I scale this by a factor of 2 in each direction, that's pretty bad. It's not like, doesn't look like 2. But if this is 2, this is 2, right? Then this is the original here. Does that make sense, Kayla?
Yes.
I was thinking, okay, so we're going to scale by 2. How many copies do we have of the original when we scale by 2? So how many copies of the original? 4. 4 copies of the original. So we're going to make some things here. So S is the scaling factor. N is going to equal the number of copies. And so this really only works on simple objects. That's why we need other methods of this. It's got to be a beautiful geometric figure that we can actually do this stuff for. Then the dimension D is defined as S to the D, the power I have to raise the scaling to get the number of copies produced. And if we solve this for D, take the natural log of both sides, pull the D out in front, this is our formula for dimension. And this is the one commonly used in simple objects with self-similarity. So why are we even talking about self-similarity? Well, let's look at that Cantor setting. Oh, well, let's actually look at one more simple example to make sure you get this. It also doesn't matter how many cuts I make in the original. So when I do this original scaling, I could have done it in any particular way. I could have cut this into thirds. And let me just do that real quick. Not officially, but imagine instead of halves, I had gone thirds, and then I scaled by a factor of 3. You can see here that yeah, I would have to scale this by a factor of 3 to get back to the original. Oh shit. Does that make sense? Yeah. And then the number of copies is 9. So we would have D here, equals natural log of the number of copies over the natural log of the scaling factor, and that's just 2. If you use this, because this is 3 squared, you can pull the 2 out in front, do all that stuff. So let's think about the Cantor set. So we've got this set, and the best you can do is just kind of fake it, you know, and make a little tiny stage 2 or 3 thing. See what you get. So let's say I cut this into thirds, or actually notice that this set here is just a scaled down version. Either one of these two is a scaled down version of the whole set. Just take a second to believe that. Look over here, think about this. If you blew this thing up by a factor of 3, so take this guy right here, scale it by 3. What's gonna happen? This is gonna stay at 0, this is gonna go to a third, this is gonna go to 2/3, so times 3. And then this is going to go to 1. And since there's just this infinite chain of holes in there that are going to blow up as well, it looks just like the original. So here we're going to use S equals 3. How many copies of the set? If I blow it up, or let's see, how did we do this? Yeah, so I cut this into 3 parts. How many copies of the set are in there?
2, right?
It's 2. Yep. So D is the natural log of 2 over the natural log of 3. And we don't use calculators in this class. But we all have them, so let's find this real quick. Natural log of 2 divided by natural log of 3 equals 0.63 approximately. Goes on and on and on. It has a fractional dimension. That's what the word fractal means. So fractional dimension. Yeah, that's about it. The word fractal, that's where that comes from. Fractal. Let's take a look at a couple other fractals and see if we can compute their dimension. Another way to think of this whole scaling factor thing is, you can think of S as the number of uniform pieces you cut it into, and then N is the number of copies that you're seeing after that cut. So for example, here, when I took this square and I cut it I scaled it by a third, or cut it into thirds. So if we had a scaling of 3, we noticed we had 9 copies when we did that. Or, yeah, cut it along, shit, the words, I gotta be careful with the words. I don't want to say dimension, cut it on each dimension. But if I cut it into, what is the word that I want to say there? Nobody can help me.
Like length?
Yeah, that sounds, yeah, but that also like falls back, yeah, right? And then all those words fall back on like dimension. And so it's a little bit scary there. Let's take a look at this next example and maybe I'll find the words. Start with a triangle, equilateral. Cut the middle third out. So remove middle third equilateral. Have you seen this construction before? Keep on doing that. So let's actually black out what we're removing. Stage 2 would be remove these. stage 3, 4, on down the way. Should have had a little demo up for us. So if I repeat this forever, I get a thing called, does anybody know what this fractal's called? Sierpinski triangle. So if I cut each side in half, so if I let S be 2, or maybe think of blowing this thing up by a factor of 2, how many copies of the original do you have? So think of it a couple ways. Blow it up by a factor of 2 along each side. Uniformly blow up the plane, the ambient plane, by 2. How many copies of this thing will I have? Or think of cutting each side, I like Kayla's, use Kayla's word, in half. How many copies do you have? Oh, how many did you say?
4.
Where's your 4? Because don't forget, this guy's gone. So if I cut each side in half, I get 3 copies. Is that Diana? You agree with that, or yeah? So what were you thinking with 4? Let's talk about that.
I think I was just thinking of not the middle.
Oh, okay. That's what I was thinking as well. Yeah. So n is going to equal 3. So the dimension of the Sierpinski triangle is log 3 over log 2. Literally the reciprocal of the dimension of the Cantor set. I don't know if that means anything. I wish it did. But this number here, let's see, I can just take reciprocal on my calculator. That's sweet. Is approximately 1.58. So it's got a dimension somewhere between, it's not a line, it's more than a line, but less than a plane. It's somewhere in the middle between a line and a plane. So here's line, here's your Sierpinski, I don't want to use greater than, but somewhere here's our triangle, and here's the plane. Somewhere between those, it's made up of a fraction, some weird combination of those two. Let me give you one to figure out. So this is what the traditional Cantor dust actually is. So let's seize the Cantor set. And I want to look at the Cartesian product here. So this is a set in the plane. Essentially what I'm going to do is I'm going to take one Cantor set and lay it here. So here's a Cantor set. Here's a Cantor set. Well, yeah, one. Here's a Cantor set. Look at all the points x, y in the plane where x is in the Cantor set and y is in the Cantor set. So let's just think a little bit about what this might look like. Let's remove the middle third here, remove the middle third here. So notice there are no points in the center of this thing, but there are the end points. So this is empty. I'm shading the empty stuff, which may, for better or worse, that's what I'm doing. And then there's no little third here, and there's no little third here, and I'm just going to do a few of these, and I think you'll believe me. So there's a hole right here, right? And then there's a hole right here, and a hole here. And if we get enough of these drawn, we can actually do this computation. And then there's lots more. Yes, ma'am?
So I don't know if this is a dumb question, but when we were doing it with the Cantor set, like once we removed the middle third, we didn't remove anything else after. So on the coordinate, like next to the big box or the big square, we're removing little squares.
Oh, right. So
Do you
why
know
is
what I'm
that?
saying? Why is it like that?
Yes, that's a damn good question. Yeah, that's. Why is that?
Because that makes sense next to the
No,
triangle.
it makes total sense, yeah.
But
Like,
it doesn't make
there
sense.
can't be any points with these coordinates, so how did I get these? Hold on. I don't think there's any answer in that book for me. I was like, look, help me. What the fuck am I thinking? Oh, because this isn't C cross C. There we go. Stop that. Stop that nonsense. Because this isn't C cross C. This is a new construction called Sierpinski carpet.
Oh, okay, perfect.
So,
I like that.
yeah, thank you. You stopped me
The
from
carpet.
lying so foully. This is a Sierpinski carpet. Start with a square. So it's kind of the 2D version of the Cantor construction. I remove the middle third of the middle square in every remaining square that exists. So now, look, we got little squares here. You remove these. It's gonna get crazy. I'm not gonna keep drawing that because that's really a waste of time. What is the dimension of that if I keep going forever and ever?
You just multiply the dimension, do you square it, or is that?
No, that's cheating. Yeah, I can't do that. Because it's not quite C cross C anyway. So, what is the dimension? And this, let me draw something that might help in terms of thinking about numbers of copies.
Shouldn't it be greater than
What's that?
I feel like it should be greater than a plane. So greater than 2.
It can't be greater than 2.
Okay. Because that one's not greater than 2.
Yeah. It won't be more than 2, but it'll be somewhere betwixt 2 and 1. How does it relate to this? That'll be the interesting question. Does it have more stuff? More stuff. Did you get it worked out, Diana? Maybe? No, okay. You see, I just felt like you were totally on this. Like you just mind melded with it. What is the scaling factor we're going to need to use to get it to map back onto itself in some way? 3, right, exactly. So S is going to be 3. You just got to figure out, if you do that, look, cut it in thirds, how many copies of the original are in there. Start actually doing the computation for the end, so I have the number. Any suggestions? Michael, what do you think?
I feel like there's 8, because that middle one, yeah, there's, yeah.
8 copies. If we cut this thing on a third on each side, how many copies of the original? Well, there's nothing in the middle, and here's a copy 2. There are 8 copies in there. Or if you blew this thing up by a factor of 3 in each dimension, you would have 8 copies of the original. So n is 8. So our dimension is log 8 over log 3, and that's 1.89 approximately. A little bit higher dimension than Sierpinski triangle. More stuff left. Not a full plane's worth of stuff by any means.
So,
Yes, sir.
all of these ones that we've done are rational numbers. Are there any that, would it even make sense to have a non-rational dimension?
Well, these are non-rational dimensions. The dimensions are non-rational. I mean, any log of anything that's not like a power of e.
Oh, because it goes on forever, we're just putting the approximate sign,
Yeah. Yeah, these are highly irrational. Yeah. What's bothering you?
7.
Okay, cool. Figured if you were being bothered, there was some deeper thing going on there. All right, that's enough dimension for today. But I think I'll create a homework problem where you have to find some dimensions. You might want to think about maybe just a fun thing. We do math for fun. That's the kind of people we are. What if you took this construction to 3 dimensions? And I'll just leave this with you. We won't go through it, and we'll maybe pick up on Wednesday. But take a cube, remove the middle third cube forever and ever and ever. What do you have left? And what is its dimension? So take this, and then just keep removing thirds. I wonder. I can't go. I got to see what C cross C is. So C cross C. Let's just look at that really quick again. So here's 1. Here's 1. Pull out the third. Pull out the third. I just want to see if we can figure out its dimension and how it relates to that Sierpinski carpet, because I think that's kind of a cool question. So C, we're going to look at C cross C. Does this have the same dimension as the Sierpinski carpet? That's what I'm wondering. It feels like it might.
I don't think so.
You don't think so?
Scaling factor. But
Okay, let's talk. So help me out here. So what do we need to scale by? It seems like 3, right? It seems like scale by 3. Multiply everything by 3 because of these original cuts. But then how many? 4 copies? Oh,
Yeah.
yeah. Because like you'd have like this little dude here, this little dude here, dude. I mean to gender the Cantor set, but.
So basically the Cantor set sweeps more out. Because that removal is not just of the center, it's of like the union of the centers. Does that make sense?
Say that again.
So you're taking out this center.
Yeah, so are
And
you
you're
talking
taking
about
out
this guy
this
here?
center, yeah.
Okay, yes.
So then it's gonna be exactly half, or close
Oh.
to half.
Yeah, close to, yeah, that makes sense.
Yeah.
That definitely makes sense. I don't think it's precisely a half, right? But
No,
it's
that would make
definitely about, so let's see, so this is gonna be log 4 over log 3. And then how does that relate? By a factor, oh, what is log 8 over log 4? So that's just 3 halves. Oh, easy.
What?
Is that okay? Michael, are you doubting that, are you concerned about that computation?
I agree on that one, the top one. I'm confused why you can go from the bottom one to the top.
Oh, no, I was looking at the ratio of these two, this dimension to that dimension, and it only matters, so that one is 3 halves times more stuff, 1.5 times more stuff than this one. That's all I was thinking about. Yes, get rid of that.
No, yeah, that's right.
Yeah. Cool.
So annoying.
So much beauty. So much beauty. But the thing is, this method does not work once you have something like the Mandelbrot set. If you don't know what that is, you need to know what that is. We're not going to spend the rest of the day talking about it because we'll spend the rest of the month talking about it. Or if you were, if you were to look at a coastline, coastlines are also fractals. There's a lot of self-similarity and infinite detail. No matter how close you zoom in, there's more. To find the dimension of a coastline, you have to use this thing called box dimension. And what you do is you cover it with little cubes of a certain dimension, and then you count how many cubes or squares or whatever are needed to cover it. And then there's a relationship between the size of the cubes and the number of cubes in limit as the cube dimension, as the cube size shrinks to 0, that gets you another dimension. That's called box dimension. Enough. I gotta stop myself. So let's talk about open and closed sets. There's a horrible math joke. Like it's in my head. It's not a joke. I would put that in quotes. It was something like, how is a set not like a door? And the joke, the punchline was that a door can only be open or closed, but a set can be, what a terrible joke. But a set can be open, closed, open and closed, closed not open not closed, or neither. So with a set, all possible combinations of open and closed are viable options for us. So let's start with just the definition of open. Set A in the reals is open if for every x in A, there exists an epsilon neighborhood around x. I'm using that notation from the book. That's just so V, here's x plus epsilon, here's x minus epsilon. That's V epsilon at x. Epsilon ball, call it epsilon ball around x, such that it is contained completely inside A. So for every single point in the set, so this is A, no matter what I pick in here, there's x, I can find a little open neighborhood around it that stays inside the set. It's kind of hard to do it with these generic examples, so let's just roll through a bunch of solid, concrete examples to make sure we get this. So the classic example is the open interval that we all know. So don't worry, everything you know about open is still true. Open interval A to B is open. Hell, it's called the open interval. Better be open, but I need a proof here. It's a proof. Take x in the set, and then let's draw a picture. Here's A, it's not in there. Here's B, and it's not in there. And then here's, say, x. Help me out, Michael.
You could take the distance from x to A and x to B and decide which is, use the minimum function, which we haven't used a lot.
Yeah.
And you can always construct it that way.
Beautiful. So look for the point that x is closest to. If there's a tie, pick either one, if x is right in the dang middle. But what we're going to do is we're going to let epsilon equal the minimum of b minus x and x minus a. Those are both positive quantities because x is greater than a, less than b. And then
Would we have to use absolute values to guarantee, because we don't know what x is?
but we do know x is in here.
Yeah.
So if I pick
Okay,
x,
okay.
if I pick x in there, I'm totally safe. I thought about that too, but then I was like, nah, we're good. We're good. Let's not introduce more stuff than we need. Then by construction, literally, the epsilon of x is contained inside AB. I'll put that there. It's strictly contained. It's not equal to it. I guess it could be. I guess it could be if x is right in the middle. It might be the whole interval. What about set like AB? What's the problem here? There's a problem. That set is not open. This says for all, so all I have to do is find one point and one epsilon neighborhood, or where every epsilon neighborhood spills out. So let's put, this is not closed. To show, you can see that A is the problem, right? The only thing I've done is add A in from the last example, so it must be the problem. To show to show this, note that any V epsilon A, draw a picture to help yourself understand what this is. So here's A, here's B, and if I pick a point here, no matter what I do, here's plus epsilon, here's minus epsilon, the left half will always spill out, no matter what. Spills out of AB on the left side. That's pretty loose language. You could say contains points that are less than A. That would be a nice mathematical way to say what I'm saying. I'm gonna write that up. What the hell? It's a freaking math class. I.e. contains points X less than A. Let me give you another. What about the real line? And what about the empty set? Let's give everybody just a second. You could think about the empty set though. That's painful. Always painful. R seems pretty chill, right? Literally anything I make in it is in it, open interval or not. So it's hard to spill out of R. Really hard with simple V. I mean, you're gonna spill out if you go to a higher dimension, but that's not what we're talking about. We're sticking in the dimension of the set. So R is open. What about the empty set? Michael? Okay, good.
I feel like it doesn't make sense to add any real number to something that doesn't exist, so it stays in the empty set, but that's my only reason why.
Yeah, this is open because the definition is vacuously satisfied. Have you heard that, like, somewhere along the ways? No? Oh, we gotta talk about that. So this is open because the definition, and when you see empty set stuff, just start thinking something must be vacuously satisfied here. The definition is vacuously satisfied because there are no points X inside there. And there are no neighborhoods that can be created. So they can't spill out. Just look this word up. Somebody should have told you that in logic and proof, hopefully at some point. But it's a great mathy thing. We're gonna see another way to understand this, so don't worry about it. Let's talk about closed. But before we talk about closed, we have to refresh our memory on something. Recall, given a subset of the reals, we say, and I'm going to ask you to see if you can cough this up out of memory. We say X is a limit point of A if, finish the definition. So I think the result you were thinking about, Michael, is that in C, every point, so if I take an X in C, it's of the form where x of I equals 0 or 2, and this is a base 3 expansion. That's where the ternary stuff comes in for sure. And it kind of makes sense because this thinks about breaking things into thirds, and you're either in the left third or the right third, never the middle third, the one. All right, friends, can someone give me this? We don't need to wait too long because you either know it or you're about to find out, and it'll be just fine. Go.
For any neighborhood around X, there is some pointing to be an A in the neighborhood.
Pretty damn close. Punctured neighborhood, that's the thing. The point itself can't count. So for all V epsilon about A minus A, so I'm actually subtracting off. So notice this is a punctured neighborhood. Let's get a notation for us. Wow. That's pretty bad spelling. Punctured neighborhood. How about we'll use this to represent punctured neighborhood, little freaking hole right in the middle. Yeah, that'll be our sign for our class. So if for every punctured neighborhood about A, V intersect A is non-empty. Every punctured neighborhood around that point touches the set in some way, no matter what epsilon is. So, we say A in R is closed if A contains all its limit points. If every limit point for that set is in the set. And let's look at an anti-example. That's the easiest way to see it. So anti-example. Counter example? Kind of. Let's let A be 0 to 1. Bless you. What are some limit points here that aren't in the set? Here's the set. So think, your limit point, if I can't move I can't move a hair's breadth left or right without spilling into the set. So every point in the set is certainly a limit point. Right? So that's a limit point because, man, it just smack dab in the middle. What about 0? Yeah, 0 is a limit point, right? Because if I put a neighborhood around 0, so V centered at 0 epsilon, that intersects the set for all epsilon. So intersect 0 to 1 is non-empty for all epsilon. Similarly for 1, you put you center a punctured neighborhood here, it spills over to the left. Over here, it's going to spill to the right. So there's your plus epsilon. Over here, it would be the minus epsilon part. But V epsilon 1 intersect 0 to 1 is non-empty for all epsilon. So 0 and 1 are limit points. But they are not in the set. So A is not closed. Is R open or closed?
Open.
Well, it's open. We know it's open. So
Yeah.
cool. Sorry, I didn't mean that. Sorry, I already said that. Is R closed? Check it's open. Is it closed too? Let me help. There's a picture of.
That doesn't make, no.
What are the limit points? What's that?
Every point, right?
Every point is a limit point. Yeah. So you take a point here. Here's x. No matter what my plus epsilon minus epsilon move away from there is, if I remove x, I still got stuff in the set. I'm still touching R. Ask some questions. You see, I see the confusion. Do you want me to kind of go through it a little bit?
Yes,
Yeah.
please.
Yes.
So,
Oh.
well, just,
Say it. Yeah, you got a nice
I
way to
know
say it.
we don't like intuitive stuff in this class.
Yeah,
but,
we hate intuitive things.
but in like complex, when we talked about close, it was like from any point you could draw a line to any. Was that?
That was connected.
Dang it, okay. I was like, maybe that'll help us.
No. So Kayla, close just means, so limit point means no matter how far I move away from that point,
Yeah.
I fall into the set. Are you getting it?
Yeah.
Oh, okay.
No, that makes sense.
Okay.
So are we saying that R is closed?
Yes.
So something can be open and closed?
Boom. Not like a door at all. That's the. Nobody's laughing, but that's the math joke. Yeah. So R is open and closed.
Nice.
What do we think about the empty set? Oh, just give it 1 second, Kelvin. Does it have any limit points?
No.
Is there anything to
Is it
intersect?
satisfied?
This is also closed. I'll give you another proof of that later. Empty set is open and closed because it literally has no limit points. Because there's no set. There's just nothing. So again, vacuously satisfied. Open and closed. These two sets are open and closed. Last one. My calc class is getting them worked up. They have an exam today, so maybe we'll just call it because they're like getting hungry out there. Hear them getting boisterous. So read section 3.2, and you'll be in really good